Ladies and gentlemen, good evening. I am Dr. I. Veeranjaneyulu, Coordinator, ALA, and it is my pleasure to welcome you to an online lecture series on emerging trends of research in electrical engineering, organized by ALA in association with Department of Electrical and Electronics Engineering, Aditya University, Surampalem. I would like to give a brief introduction to our university, which is providing a dynamic learning platform for enthusiastic learners. Aditya University is a place where students can grow academically and personally. Here, education is not just about earning a degree. It's about discovering your potential and preparing for a meaningful future. With students from over 20 countries, the campus is a diverse and lively community that encourages new ideas and teamwork. This international environment helps students get ready for careers worldwide. At Aditya University, you will gain the skills to make a real difference. I would like to give a brief introduction our Aditya Learning Academy, a center for teaching and learning at Aditya University under the name Aditya Learning Academy, is established to advancing teaching and learning through specialized certification courses. Recently, Aditya Learning Academy successfully organized two online certification courses. One is Machine Learning and Generative AI, scheduled from 5th June to 16th August 2024. And we had received 1650 registrations. Second one is Data Visualization with Power BI and Tableau, scheduled from 23rd September to 4th October 2024. We had received 680 participants. Both courses reflect ALA's commitment to providing high quality in demand skills training. Today we are going to begin an exciting journey where you will explore emerging trends of research in electrical engineering and develop valuable skills to enhance your professional and personal growth. Over the next 10 days, you will engage with our expertise resource persons to gain insights into field of electrical engineering. Our course is designed to provide with a comprehensive understanding of optimization techniques, MATLAB, EV applications, modeling of facts, devices, and practical applications. Finally, I request Dr. Rambabu N, today's resource person for this online lecture series, to take over the session. Thank you.
I would like to thank Dr. Ivy sir for your warm introduction. Myself, Dr. Naladi Rambabu. Currently, I was working as an assistant professor in the Department of Electrical and Electronics Engineering at the University of Surampalem. So, I would like to welcome all the participants for the 10-day certification course on emerging trends of research in electrical engineering. Coming to the resource persons, first myself, followed by Dr. K. Bapanayadu Garu, Associate Professor in the Department of Electrical Engineering, and next Dr. V. Srinivasarao Garu, Associate Professor and HOD in the Department of Electrical Engineering. At first, I would like to thank Dr. M. Srinivas Reddy Garu, Deputy Pro Chancellor of Aditya University, for giving us this opportunity for the smooth conduction of this certification course. Next, I would like to thank Dr. Ramasri Madam Garu Deputy Pro Vice Chancellor of Aditya University, for the continuous encouragement and support towards the certification course. Also, I would like to thank Dr. V. Srinivasarao garu, Head of the Department, for choosing me as a resource person. As stated earlier by Dr. Ravi sir, earlier two certification courses were made grand success by our participant. I request the participants of today's event to make this event a grand success. A total of 200 participants have registered for this unit. Hope this certification course will gives you a lot of knowledge and share its experience. So before going to start my presentation, I would like to thank Dr. Ralchandra Saikya garu, who is my PhD guide. Uh, Through his continuous support and guidance, I was at this position. So coming to my biography, I did my PhD and M.Tech from National Institute of Technology, Silchar, under the esteemed guidance of Dr. Ralchandra Saikya, who is renowned as a world's top 2% scientist in the world for the past 5 years. Apart from my personal experience, coming to my research profile, I am on my name, 2 Australian patents were granted. Okay, apart from Australian patents, 1 Indian patent was published on my name. And coming to publications part, around 76 publications were there on my name, out of which 24 articles are SCI articles and 7 are Scopus indexed journals, and 8 articles are published in book chapters. Apart from that, I have published around 14 articles in Springer book chapters and 21 IEEE conferences. You can observe that from my Google Scholar profile, I am having around citations of 16 and H index of 12 and H index of 21. Apart from that Google Scholar profile, here you can see that I am having around 71 publications as of now in the Scopus database. Now coming to the contents, it is a total 10-day course in which first 4 days will be shared by me. The contents are introduction to MATLAB and its modeling perspective. And in day 2, I am dealing with studies on automatic generation control system. And coming to day 3, concepts of virtual power plant. And in day 4, role of optimization techniques in electrical engineering. And from day 5 onwards, Dr. K. Bapanaidu garu, Associate Professor in Electrical Department, will share his knowledge. And on day 5, he is dealing with effective control schemes of brushless DC motor for electrical EV applications. And in that, he will completely describe around mathematical modeling and its conventional controller. And coming to module 2, that is in day 6, he will be presenting you a converter topology for power factor improvement. And on day 7, he is dealing with speed control of brushless DC motor with fuzzy logic control systems. And coming to the third phase, from day 8 to day 10, our HOD sir, Dr. V. Srinivasarao garu, will share his knowledge experiences. On day 8, that is on 14th of November, he will be dealing with mathematical modeling of fax devices, and in that, optimal placement of TCSC and TCPAR. And coming to module 2, he will be teaching us optimal placement of UPFC and IPFC. And on day 3, that means on last day, 16th November, he will be presenting us parameter setting of TCSC, TCPAR, and UPFC. So in completely out of these 3 resource persons, you can observe that we are dealing with power systems, control systems, and also with power alternative devices. And recent trends like optimization techniques in the electric vehicles and control technologies are also being taught for us. Now let us go to the first section, day 1 topics. The topic is MATLAB for engineers at foundation level. So the contents are, first one is introduction, next one need for MATLAB software, necessity of controllers and types of controllers, applications of controllers, and hands-on training session. The thing is, whatever the technology which I have told so far, we are completely working on the MATLAB software. Why we need this software? Maybe a few people know about the MATLAB full form. Let us tell me again. The full form of MATLAB is Matrix Laboratory. That means we are dealing with all the elements of a power system or power electronics or anything in a matrix form. So in that matrix form, we all know that as a power system student, Z bus, Y bus kinds of thing. In Y-bus, almost all the elements will be 0, which is called a spares matrix, which makes us to provide the calculations part very efficiently and very easy. So coming to this, we are dealing with MATLAB, and in this section itself only, I will be providing you a hands-off training if time permits and time is there. Okay. Now let us go in depth. What is meant by MATLAB? I have told you. Next part is the recent trends in MATLAB. Why we need the MATLAB? First one is MATLAB is used for statistical and machine learning. The first one is statistics and machine learning. We can observe that we can deal with all kinds of mathematical problems like rank of a matrix, pairs, sparse, all the things we can get with the help of the statistic model toolbox. And the next one is machine learning toolbox. That means we can provide, we can give some knowledge to the machine so that it can provide us effective knowledge and all the things. So the first thing is toolbox. So in toolbox, we will be getting all kinds of informations in which we will be using it for simulation and simulating purposes. Firstly, before going to the MATLAB works on two domains. The first one is simulating profile and the second one is simulation domain. In simulating domain, we will be designing a mathematical model. That means we will be developing a mathematical box and we will working on it, like modeling of electric vehicle or modeling of TCSP or modeling of automatic load conversion system. These things we are going to develop in the MATLAB in simulating profile. Whereas coming to the simulation model, it completely deals with coding part, like how many buses are there in system, or else load power flow analysis, or Z bus calculation, or Y bus calculation kind of thing. We are going to get in the in the Simulink file. That means it completely deals with coding part. Next toolbox is curve fitting. So curve fitting in the sense, we know the objective of a function and that function should reach the minimization case or maximization case. In order to get the minimization curve or the maximization curve, whatever the curve which we have developed is to be fitted into that certain position. So for that purpose also, this curve fitting toolbox in a MATLAB, we will be going to use it. And the next part is control systems, in which now I am going to deal the part control systems. As we all know that control system, we need to control something. So that controlling part, that mathematical modeling and block diagram part, we will be getting to know in the upcoming sessions. And the next one is signal processing. The signal processing means we are transferring data in the form of voice or image or some signals being transmitted from one place to another place. In that places, some amount of data may be missing. So we are using this MATLAB software for all this kind of transform techniques. And the next one is mapping. So coming to the mapping, it deals with theft analysis. That means it deals with regression models and contingency analysis in such a way that what are the element we have lost or what are the element which we have which was dissolved during any murder scene or some other scene crime offenses. This mapping technique is very much used in order to get the data and to provide us with an efficient manner. Next element is deep learning. So it is a subset, it's a subclass of this machine learning which provides us speech recognition tools. Okay, which provides us speech recognition tools, financial fraud detection, and medical imagings. It also deals with fuzzy networks and artificial neural networks in a system. And coming to the next one, financial analysis. Our it is also a toolbox. Oh, it is also a toolbox in which we can solve the in which we can do the financial mathematics models in order to get the liquidity, stability, profits, and losses. We can calculate by using this financial analysis process. And the next one is image processing. Coming to this image processing, the blurriness or the background effect or face detection, it can be done with the help of MATLAB by using this image processing toolbox. Also, with this we can recognize faces and some detection and some image enhancement also can be done with the help of this image processing. And the next feature of the MATLAB is text analysis. So generally, our Grammarly does the grammatical mistakes in the system, or else many softwares will be doing the text analysis. But whereas in MATLAB, we can find the text analysis, text sentiment. Sentimental analysis can be done with the help of this MATLAB. And the next one is electrical vehicle design. As I have stated earlier, with the help of Simulink model, we can develop and design a mathematical model. Similarly, in the sense, we are going to develop the electric vehicle. That means we are going to design the electric vehicles in the MATLAB, such a way that the battery consumption ratio, the charging coefficient and discharging coefficients, all these things will be discussed by our fellow, our another resource person, Dr. K. Bapanadu Garu. Next one is aerospace toolbox. So in this aerospace toolbox, we can get the data and we can analyze the aerodynamics of an aeroplane or aircraft, and then we can get the navigator for the Simulink file. That means flight simulator also we can get it with the help of this aerospace block. Next one is audio toolbox. As like other softwares, this MATLAB also provides audio processing signals and speech analysis. That means it will use the audio processing signals and speech analysis, and also measures the acoustic measurements. So these are some of the elements that which we come across the MATLAB software. Next, need for MATLAB. What is the need for MATLAB? In general, we all know that MATLAB is a software which is going to be used by students and researchers and the faculty members for developing or designing a new thing. Apart from that, here I have mentioned some of the some of the items that are needed that will be helpful for the MATLAB software. First one is data analysis. As I have stated, the financial and statistical analysis, this MATLAB has an inbuilt function which includes optimization, linear algebra, and signal processing. We all know that optimization means the controller optimization or minimization case or maximization case in which errors can be minimized, and maximization case in which profits can be maximized can be done with the help of this data processing element. And also linear algebra. We all know that ax plus by equal to c and some other functions a1x plus b1y equal to c or a2x plus b2y equal to c. There we can get the elements of values of x and y with the help of this MATLAB very easily. And also signal processing. Next one is algorithm development. This MATLAB helps us to develop new algorithms. In my research study, I have developed two different kinds of new algorithms. First one is hybrid genetic algorithm with particle swarm optimization, and the next one is hybrid radial movement algorithm with arithmetic optimization algorithm. So we have done this. Like this, many algorithms can be developed, and most importantly, these algorithms are readily available. That means some of the algorithms are readily available in a MathWorks open source web link. You can download the softwares, and the most important thing is you need to connect the algorithm to your prescribed system. That is the major thing, which we will be discussing it on the fourth day of our lecture. The next one is simulation. As I have stated earlier, we will be simulating the systems and developing a model and designing a controller part. All these things will come under the simulation part. At the first instant only, I have told you that this MATLAB is used for teaching and research. So the thing is, for teachers, it is helpful it is helpful to teach the students and to know them the advanced knowledge. And for research scholars, it's helpful for writing research articles and all the things. Next one is the most important thing is integration of this MATLAB with other languages. This is the major thing which a very few people will be knowing. Actually, in my PhD, that means during the course of PhD, which I have done from 2017 to 2021, I have intercoursed this MATLAB software with real-time lab simulator software, and we have published around 2 to 3 essay papers on that on that ground. Apart from that, apart from that, this MATLAB can be interlinked with other software such as Python, Java, and we can get the best and desired output results from this MATLAB. So here I have provided the brief features of the MATLAB and its capabilities. So as I have stated earlier, the MATLAB is a programming language in which it contains inbuilt user functions, that means built-in functions, in which it contains the graphics, computations, and external interfaces. Coming to the graphics part, it gives us the images in 2D format, that means length and breadth, like power versus time graphics, power versus time graph, or current versus time graph, or some x versus y graph. And coming to this 3D graphics, it provides coming to 3D graphics, it provides the images in 3D form. That means length, breadth, and height, like ultramagnetic wave radiation kind of thing. Next one is coloring and lighting. It is an user, as I have told you that our MATLAB is user-friendly software. It provides coloring, lightning, and stroking effect with the result part. Next one is animations. Our MATLAB software will also provide animations. Next one is audio and video. As we know that this MATLAB has an external feature that provides with the audio and video kind of thing. Next one is computations. That means mathematical computations. First one is linear algebra. It helps us to solve linear algebra functions. Next one is data analytics. As I stated earlier, statistics, probability, and financial problems can be solved with the help of this MATLAB. Next one is signal processing, followed by polynomials interpretation, quadrature, and solutions of ODEs. Apart from this, the external interface like we can interface our MATLAB with real-time simulator lab, Java, Python, C program also. Actually, our plan is to implement. Actually, we are working on implementing interfacing of MATLAB software with Python. Maybe in a few days we will be doing it and we will be succeeding in it. And the next one is toolboxes. As I have stated earlier, our MATLAB consists of some toolboxes. It consists of single processing toolbox, and the one is statistic toolbox, control system toolbox, system identification, symbolic mathematics, and M analysis. Neural networks is another toolbox will be there, and we also know that fractional order another toolbox will be there. So and image processing and optimization case also some toolbox will be there. So if we have this toolbox in our MATLAB, we can easily work on our desired responses and output. So here are some of the need for the MATLAB softwares. Now let us go into necessity of controllers. So as I have stated earlier, I am dealing with controllers. First of all, we are supposed to know what is a controller, and this part we will be coming in the next slide. Before going to that, why we need controller part we should know. As I have told, controlling has become a very important function. For example, I need to turn on the switch with a remote. This is also on control technology. As I'm speaking it now, my voice should be amplified with the microphone. This is also one of the control technology. It means by what actions it should be amplified. So these all things will come under controllers. Apart from that real time, here I have mentioned some of the real time necessity of controllers. The first one is accomplishing organizational goals. That means we are having an organization. Let us say that research is one of our goal in our organization. We need to publish some number of papers. For that, some accuracy or some number of papers is to be published. Our goal is to produce more number of research articles. For that, we are working on it with the help of MATLAB software kind of thing. Or else, in order to accomplish our goals, this control is required. That means I need to turn on this fan. In order to turn on this fan, turning on this fan is my goal. For that, one control technique is required. That means a normal switch which consists of a PN diode, PN junction diode, which acts as a switch. This is one of the control technique. Next one is depending upon judging accuracy and standards. So the control part is mainly used to reduce the error, isn't it? We all know that the control part is mainly used for reducing the error quantity. If error gets reduced, the accuracy of the system will be increasing. So we will be working on reducing the error and improving the accuracy and the system standards. Next one is making efficient use of resources. Suppose a 3-pin multiplex box is there, a 3-pin multiplex box. In that, number of sockets will be, let us assume that 3 sockets are used. Or else forget about this, let us go for demand side management technique. In the demand side management, we will be working with Wi-Fi technology, Wi-Fi and Bluetooth technology and GSM technology. With GSM technology, if we send a message, the another mobile or SIM will receive it and it automatically turns on or off the respective device. So the thing is efficient. We need, without going to that position or to manually turning on, with the help of this GSM and GPS technology in the demand side management technique, we can turn on the equipments efficiently, like dishwasher turning on the dishwasher, turning on the washing machine, kind of things. Next one is facilitating the coordination, in action. Next one is improving employee motivation. With this better resource, the motivation of an employee can be improved. Final one is ensuring order and discipline. Now, where this controller part will be used? If you want to say this part exactly, the first part is industry part, second one is at computing resources, and the third one is finance. And coming to industry, if you want to go with an example, in an industry, let us assume an industry where temperature is to be maintained constant, or else let us have a bike or a car which is turned on for a long time. If it is turned on for a long time, there won't be any problem. But if the machine runs for a long time, then the temperature of the system or a car will be gets heated up, isn't it? So if the temperature of the machine or the system gets heated up and it is running for a long time, our system gets damaged. So in order to reduce the temperature and increase the efficiency of the system, this control is increased. Getting my point? Another one is pressure. Similarly, force and flow rate. These techniques are used in the industry to improve the accuracy, stability of a system. Next, followed by computing technologies. So these controllers and drivers are connected to computers, are often connected to devices and its applications, extending the functionality of an operating systems. I think in the next class, I will be dealing with low frequency control system, where the controller is having some parameters, and these parameters will be optimized with some of the algorithms, and that part we will be discussing in the next session. Next, followed by finance. As we all know that this is having some statistical toolbox. This helps in developing those things. Okay. Now let us go in detail saying that what is a controller. As we all know that it is a device or an instrument used to achieve a specific objective. Are you getting my point? It is a device which is developed or designed to achieve a specific object, which is called as controller. In order to gain for simply for understanding purpose, I have given you one example. We all know that this is the screen of a mobile, isn't it? If you look into this mobile, here another one option is there called automatic brightness. Okay. Oh, sorry. This is automatic brightness option. The thing is, if you are in home, that means not in sun, our mobile will automatically adjust its brightness to our room conditions. If we go outside the room, that means in sun or cloudy conditions, again this brightness will automatically gets reduced or increased to our normal operating eye condition. This is done by a control technique. Okay, this is done by a control technique. This is one of the example. Let us go with another example, that is automatic water control system, which is installed in our overhead tank. In our homes, we are having an overhead tank which is filled with water. There you can observe this kind of a mechanism system. These are some of the immersion rods which are inserted in water, and this is installed at the top of a water overhead tank. The duty of this overhead tank is it senses the level of water in an overhead tank, and based on that this machine will operate. For example, if the level of water is less, this machine will that means this device will automatically gets turned on and helps us to fill the water in the overhead tank. Or else, if the water in the overhead tank is full, very much full, this machine, this device or instrument senses the level of water, and if it is found to be the level of water is at a certain level, this machine automatically sends a signal to the motor to turn off. Are you getting my point? So these are some of the examples. Apart from that, I have given another example, that is robot mechanism. If you observe this, that means nowadays with the increase in AI technology or AI, robots are being developed in a very efficient manner. So these robots, we will be giving some objective. Maybe some objective is to serve in restaurants, or to go for certain place, or to transfer or to transport some for transportation purpose. Here we have designed a robot which its motive is to walk, that means to travel for certain distance, isn't it? That means, or else I will give an example saying that a room cleaning robot, we will be simply calling it as some machine which cleans the room. Okay, so these are some of the examples. These these are the devices which are installed in this respective applications, and this mainly does to detect the temperature, pressure, force, flow, etc. kind of things. This works on pressure, so this works on flow rate, and this image, this electronic display, it works on temperature or brightness kind of thing, and this works on distance. Okay, now let us go into the block diagram of a controller. If you observe this one, this is the block diagram of a controller part, where controller is placed at the center. After the controller, we can simply call this as this actuator and process as a plant. Okay, and for this controller, the feedback, we are getting the feedback from the sensor. That means the temperature, maybe it may be called as temperature sensor or pressure sensor, a flow rate sensor. So sensor, and this will be reference signal or input closing the path. See, this is the input or reference signal, and this is the position of the controller, and this controller is getting input from the reference signal and the error, nothing but feedback signal. Here it will be the error, and this is the feedback signal. That means this error is the combination of input signal and the reference signal, and this part is called the output path, in which we are getting the output may be displayed. So this is the general conventional diagram. This is a general conventional diagram of a controller loop. This is the open loop control system, but in the next class, in the next slides, we'll be going for closed loop and open loop and its types of applications one by one. The thing is, we need to know what were the functions of this controller. If you observe this here, this controller gets error as an input signal, which compares the relationship between set point and the feedback signal. You are getting? This is the error input of the controller. This error sets the reference points between the set point and the feedback signal, and also it calculates the quantity of error which is to be minimized. And next one, it is the signal corresponding to the quantity, and also it produces an output with less value of error with highest accuracy. Okay, now coming to the next topic, the topic is types of controllers. As I've told earlier, that the block diagram is of closed loop control system. If closed loop control system exists, an open loop control system also exists, right? So let us go in detail about these two controllers, two types of controllers. The first one is open loop control system, and the second one is closed loop control system. So coming to the block diagram of open loop control system, here somewhere controller is placed. The controller is placed in front of the plant. That means here I have considered the motor. My position, my motive is, that means my objective is to reduce the speed of a motor. Okay. For that I have placed one controller, and for that controller we are giving some input. The output of the controller is going to the motor, and from motor we are getting the output. For this, let us take an example of saying that some roller coaster. That means a machine with a motor, a remote car. If you press a button on the remote car, it will turn on until another button is pressed for the off position. That means we are supposed to give the output signal manually. This is the open loop system. In open loop system, there is no influence of control action. So here I have provided some of the examples of the open loop control system. The first one is traffic light signal. Second one is washing machine in our home, coffee maker, and the bread toaster, emulsion coil, and the bulb. So let us go in detail. As I told earlier, this signal light is an open loop function. Let us discuss about it. Suppose if people are traveling on the road, and if many people are came across these traffic lights at the junctions. Maybe in a heavy or rush area, that means rush timings or busy timings, if people maybe calculate the time 49, 50 or else 50, 49, 48 kind of thing. Until you get the green light, you are not supposed to go. Okay. But even if you go at the night time, even when the road is also empty, you are getting my point. When the road is empty at night times, at that time also, these traffic lights will glow on continuously saying that 49 seconds, 50 seconds, we have to wait it. That means this traffic light signal doesn't have any control on the output. That means for 50 seconds it will turn on, another 50 seconds it will turn off. This is the duty. That means there is no control of the signal. Next one is washing machine. Even in the washing machine also, if you observe that, many options will be there: hot water, cold water, and timer also. 1 hour, 30 minutes, or 50 minutes kind of thing. Timer is also there. Our objective is to wash the clothes. So for that, we are opening the lid of the washing machine and we are keeping our clothes inside it, and we are pouring um, some liquid detergent into it, and we are turning on the switch, and we are choosing some options. Let the option may be for 30 seconds. Okay, that means till 30 seconds the washing machine will be in on position. That means it continuously doing its work. It doesn't matter whether the clothes inside the washing machine have removed all the dirt or not. Are you getting my point? But the main objective is the clothes in the washing machine should remove all the dirt, but it doesn't concentrate on the dirt on the clothes. It will rotate continuously till its prescribed time has reached its maximum level. Once after reaching the maximum time limit, then it automatically gets turned off. So there is no control mechanism for that. Next, the coffee maker in our home. If you look into a coffee maker, the objective which we are supposed to do is to fill the glass with a cup of coffee or tea. We'll be just keeping our cup at this position and turning on the switch. But inside before that, we are keeping what quantity of liquid has to be come to the cup. Let it be 20 ml or 30 ml or 40 ml. Okay, that means if you press the button, even though the cup is there or not, the coffee comes down. You can observe this in at our railway stations or at our offices also. Just if you press the button, the coffee will go off, will come out of the machine, but it doesn't check whether the cup is here or not. Okay, and the next one is bread toaster. This bread toaster also, we are keeping the bread loaves in this machine and pressing the switch. Okay, there the thing is, our motive is to fry the bread. But what will happen till the timer? The bread will get, sometimes the bread will come out of the machine with black color. So there is no control mechanism for this also. And even these two, last two, probably we will be coming across in our homes. First one is immersion rod. Okay, many people in our hostel has gone through this immersion rod. So if you look into this immersion rod, we will be placing this immersion rod in a bucket of water, and we will be turning on the switch. Until or unless you turn off the switch, the immersion rod will be in on position only. Until you turn off the switch, then only the immersion rod will be off and the water gets, that means the heating of the water gets stopped. Even in the case of bulb also, until unless you turn off the switch, the bulb will be in on position. It doesn't check whether it is daytime or night time. Are you getting my point? So these are some of the things of open loop system in which the output has no significant effect on the input. Next one, closed loop control system. In the closed loop control system, the output of the system is given as input with some feedback control mechanism in which the desired output response will be getting. So if you look into this structural diagram, here it is the controller part, and this is the motor in which output is to be reduced. That means the speed of the output is to be maintained constant, and this is the feedback mechanism. So from the output, a feedback mechanism will be there. The feedback mechanism will collect the data and it will give the input as input to the controller. Okay, here the controller error which makes the difference between the command value and the feedback signal, and it tries to reduces the output. Sorry, it tries to reduces the error by changing the controller settings. Okay, in such a way that the desired output response for the system is speed control. The speed of the DC motor is to be maintained constant. Okay, for this also I have given some of the examples. The first one is our water heater in our washrooms, and the next one is AC air compressors, followed by iron boxes, electrical ovens. So if you look into this water heater in our installed in our homes, if water gets filled, you are supposed to turn on the water heater by turning on the switch. Okay, once you turn on the switch, if the water reaches some prescribed heat like 100 degrees centigrade or 40 degrees centigrade, once the entire water in this water heater gets heated up to 40 degrees or 50 degrees centigrade, this water heater gets automatically turned off. Even though the switch is in on position, the water in the in this machine will be stopped heating. But due to its technology, upcoming technology, the temperature of the water in this machine will remain constant. Okay. Next one is AC. We all know that this AC, our air conditioners are having some sensors. If the temperature of this of our room is to be cooled down, we are keeping the temperature of AC as 23 or 24 or 25 degrees centigrade. So let us assume that I have kept the temperature of AC as 23 degrees centigrade so that my room gets cooled. Once the room temperature gets cooled down to 23 degrees centigrade, the AC in our homes will get automatically turned off. When or will get turned off? When if you see if the machine senses the rising temperature of the room, again it automatically gets turned on. Okay, you may be observing this in the case of ACs. Next one is our iron boxes. These iron boxes, we are having some knobs, temperature adjustments. If you are using it continuously, the iron box will be on position. If you are keeping it aside from some time, and if the temperature reaches maximum amount of the thing, the iron box stops working for some time. After that, again it will start heating the iron box. That means it is analogous to this AC. Similarly, in the case of our micro ovens also. That means with the help of this, closed loop controllers, closed loop control system, the output of the system, we are controlling the output of the system by reducing the error in such a way that the efficiency of the system has been improved. In the previous slide, I have discussed about this immersion rod. Okay, until unless the switch is off as manually, it will be in on position till the water gets it will be in on position, the water gets heated continuously. But in the case of this water heater, the temperature gets fall down and the water heater gets working stopped. The water heater gets stopped working. Okay, this is the major difference between the open loop and closed loop controllers. Next one, types of controllers. Previously, we have discussed about the controller system based upon their structure, that means outer open loop or closed loop system. But here, while coming in terms of research, the controllers have been classified in these terms, and some other controls are also there. But most probably, we will be knowing across these controllers in this session. The first controller part is integer order control system. Okay, and the second one is fractional order control system. The third one is tilt order control systems. Fourth one is degree of freedom control system. Fifth one is intelligent control, and sixth one is cascade control systems. Here I have given you the examples. Integer order control systems, P, PI, PID, and PIDN are the types of integer order control systems. And next one is fractional order control systems, FOPI, fractional order proportional integral, FOPID, fractional order proportional integral derivative, and the third one is fractional order proportional integral derivative with filter coefficient. Okay, that means in the next sessions we will coming to know the detailed structure diagram also. The third one is tilt order control system. In tilt order controls, TI, that is tilt integral control system. Next one is TID, tilt integral derivative control system. And next one is TIDN, tilt integral derivative with filter coefficient. And the fourth one is degree of freedom controllers. As well, these three are some kind of controllers, some conventional kind of controllers. Whereas coming to the degree of freedom controllers, it is having two inputs. Okay, if the controller is having one input, it is called as one degree of controller, which is similar to integer order, fractional order, and tilt order controllers. And next one is if the controller is having two inputs, that means two reference points are set points. Are you getting my point? Suppose in this PID controller, you will be having only one reference point. That means one input. Whereas this degree of freedom controllers, two degree of freedom controller in the sense two reference points. Okay. we will be coming to know it detailed in the sense. For example, in PID controller, our motive is to keep the motor at constant speed. So therefore, some maximum value will be given. Whereas coming to 2 degree of freedom controller, it will be having two reference points. The first reference point may be the lowest value, and the second reference point may be the highest value. Similarly, in the case of 3 degree of freedom controller, three reference points will be there. Whereas the conventional controllers are having only one reference point. That means all the controllers are having one reference point except degree of freedom controllers. And the fifth one is intelligent controllers. We all know that the upcoming technologies with intelligent artificial intelligence techniques, they are fuzzy control, neural networks things, and model predictive control. One more control is there. It will predict the model of the system. And the sixth one is cascade controllers. Here the cascade control in the sense the combinations of any of the above. That means maybe the combination of PI with PID, or else FOPI with PID, or TI with PID. Like that, many combinations will be there with the help of these cascade controllers, which are suitable for certain application purposes. So now let us go in detail of the PID controllers. At first instant, we will be going through the proportional term, integral term, and derivative term one by one. And after that, we will be going in detail with integral order controllers and its applications. That means types of controllers and its applications in real-time world in terms of research perspective and in real-time perspective. The first one is in PID controller. The first element will be the proportional term. So before going to this term, let us go in the block diagram of PID controller. Okay, see, this is the structure of PID controller where P means proportional, I means integral, D means derivative. Okay, so in proportional controller, whatever the error we are getting, this is the error E of t. Whatever error we are getting, this error is multiplied with, sorry, this error is multiplied with this proportional term. That means, suppose if the error is 0.1 and the proportional gain value is 1, it will be multiplied in such a way that 1 into 0.1. Or else if the proportional value is around 0.1 again, this 0.1, let us assume that E of t is 0.1. Okay, this proportional value is 1 and assume that I and D are 0. Okay, so the thing is the output of this P controller is 1 into 0.1. That means it will here will be getting the value of 0.1. That means the error gets multiplied. Or else let us take this value as 2. Okay, that means the output of this proportional controller is 0.1 into 2, that is 0.2. That means in the sense the error of the function, the error of the system is getting multiplied with the proportional term, isn't it? So next, coming to the integral term, this part. In this, assume that the value of P and D are 0. Okay, assume that the value of P and D are 0, and here in this part, let us take at the first instant the error value is 0.1. Okay, whenever it comes to error, our main motive is the error value is to be minimized in such a way that the accuracy of the function is to be improved. Okay, so now here what is doing this integral function? It is ki. If ki, let us take the ki value as 1. Okay, it is 1 into integral of 0.1 dt. That means whatever the error we are getting, it is multiplying with, it is getting integrated with the error. Let us assume another function called as 0.1s. Okay, let it be 0.1s. Here, if I integrate a constant, if I integrate a constant, the value will be again 0.1 into s here. For 0.1 into s, it will be 0.1 into s square by 2. That means the error value is getting integrated continuously. If it happens so, What will happen will come in the next slides. And let us go with the D term. When you are considering the derivative term, assume the values of P and I are 0. So if P and I are 0, only derivative term will be there, and here summation blocks are there. If you observe it, here are the summation blocks. So if the error is 0.1, like in the previous cases, okay, this derivative block, what will it will does, you know, here it is having some gain. KD means some gain. Let us assume the gain of the derivative block is 1 at the first case. Okay, now 1 into d by dt of 0.1. That means a differentiative of a constant value is 0. Okay, are you getting it? Or else let us take an error function which is in the value of 0.1 into s. Now see here, as the derivative gain is 1, d by dt of 0.1 into s, that is, we are differentiating s with respect to t. That means it will be in the value of 1 into 0.1, which is nothing but 0.1. Okay, so like this, the error values we will be getting. For proportional gain, the error is getting multiplied. For integral gain, the error is getting integrative of the time, and for derivative gain, the output will be the error will be the derivative of the respective times. And now we will take a 10 minutes break. Welcome back to our second session. Previously, we are discussing about PID controller part, and that how the error is going to be after the PID control part we have seen. Now let us see the value of error with P controller separately, I controller separately, and D controller separately. So now let us look into the P controller part. So as I told earlier, P means proportional controller. So in proportional controller, the error gets multiplied with of the gain, with the gain Kp. So now see here. Here we have drawn the plot between time x-axis time in seconds and y-axis in amplitude of the signal. If you observe this one, the square wave path is there, isn't it? This is called as, we have considered as a reference signal. Apart from that, this one, the curved path, I have considered at the Kp value at 0.5. That means the gain of proportional constant when it is 0.5, we are getting an underdamped signal. When the Kp value is 1.1, it is reaching above the reference signal. Okay. When the Kp value is 1.1, the value is reaching above the signal. So now I think you can clearly see from this here. Now see here, I have taken this as reference signal. This one is the reference signal. Okay. In that, if the Kp value is 0.5, that means we are getting an underdamped signal. That means the proportional value is 0.5, underdamped signal is getting. If Kp is equal to 1.1, we are getting the signal, an oscillation signal, and which is settling somewhere when settling far less when compared with Ki value is 0.5. Next one, I have increased the Kp value to 1.6. If the Kp value is 1.6, my oscillations has been increased to 1.6. That means the peak overshoot has increased to 1.6, and peak undershoot has fallen down to around 0.6. That means my Kp value is increasing, the peak overshoot and peak undershoot values are increasing. Also, the settling time is also increasing. So if you observe this one, if Kp is 0.5 underdamped and Kp is around 1.1, somewhere it will be known as critically damped kind of condition we are getting. And if the Kp value is greater than around 1.6, the peak overshoot and peak undershoot values are very much high. So our main motive is we are supposed to reduce the error in such a way that the Kp value should be optimum. Regarding this optimization case and conditions, we will be discussing in the third day of our certification course. Okay. So overall, the conclusion is if the Kp value is less, the system is unstable condition. Sorry, system is underdamped condition. And if the Kp value is very high, the oscillations in the system are increasing and it is leading to instability condition. Okay. Here, this is the reference signal for the Kp. Next, followed by Ki, that is integer order controller. During this integer order controller, that means the same block diagram we are considering. In this, I have kept this Kp value at 0.1, even Kp value at unity, and Kd value is at unity. And most importantly, I forgot to say that in PID controller, the proportional integral and derivative terms will be the summation of this error. So this is the error you are getting, and all these are getting summation over here. This is the P term, K term, I term, and D term. All the errors are getting summation. So if you in the integer controller part, I have considered Kp value as 1 and Kd value as 1. Now we are dealing with the integral term. So coming to the integral term, whatever the error we are giving is getting integrative of that error. That means after this integral term here, somewhere here, the error is multiplied with integral gain with of error. Suppose if we are getting the integral error as 1, after integration the value will be x, or else if we are getting the integration, the error is as x, after integration we will be getting the value as x square by 2. Like that, the error is getting integrated. And here also we have drawn the plot for various values of integral error. If you look into this part, we have observed that here okay. So this is the signal. Okay, this is the graph for only integral part when proportional and derivative gains are kept at unity. So here also the x-axis is time and the y-axis is amplitude of the signal. So amplitude of the error signal. So if you observe this one, this blue color one is called as the reference signal. That means I have considered a unity step input. Afterwards, when Ki is equal to 0.5, we are getting an underdamped signal. When Ki is equal to 1, we are getting a critically damped system, and when Ki is equal to 2, I am getting an overdamped system where the peak overshoot and peak undershoot of the system are very much high. That means even in the case of integral controller also, okay, even in the case of integral controller also, higher values of Ki leads to instability case. That means steady state error is increasing. Next, we are moving on to derivative control part. In derivative controller, we are considering the proportional value. That means we are keeping the proportional value and integral gain value at unity. Now moving on to derivative controller, that means 1 plus 1, that means 1 plus Ki of integral of 1, that means x, and with dig. Now let us assume we are getting the error value of x. Okay, if I differentiate that x with respect to time t, the output of the derivative controller is 1. Okay, or else let us take another example. The error value is a constant value, let it be 0.1. After the derivative gain, the value will be differentiative of 0.1. That means we are differentiating a constant value. It will be 0. Getting my point? But the output of this integral derivative controller, it should not be 0. If it is 0 means we are creating an unwanted disturbance in the system. Okay, that means the presence of derivative controller in the system provides a noisy and unwanted unwanted signals which are supposed to be eliminated. And this elimination path we will be discussing in the next slides. Okay, now let us look into the plots of this derivative gain. So this is the plot for the derivative gain. Here also we have observed that on the x-axis we have taken time in seconds, and on the y-axis the amplitude of the error. So if you look into this one, here I have considered the Kp and Ki values as unity. That means Kp proportional gain and integral gains values are at unity, and derivative gain we are varying. For the first instant, I have considered derivative gain at 0.5. So if the derivative gain is 0.5, I am getting the peak overshoot and peak undershoot. And next instant, I have considered derivative gain at 1. Okay, in that case also, I am getting the peak overshoot case and peak undershoot case, but which the values are less when compared with 0.5. Similarly, I have considered the derivative gain value at 2. So at 2, at given gain is equal to 2, we are getting the peak overshoot at around somewhere 7 seconds. That means the value of peak overshoot is getting moved when the derivative gain values are increasing. Okay. So here are some of the key points which are need to be discussed. Okay. When due to the derivative concept, due to derivative controller gain, a noise and unwanted signals are to be introduced because of constant signals. So which is to be nullified. Next one. Here I have shown you the case where the rise of Kp, Ki and K means integral proportional gain, integral gain and derivative gain values with respect to time. Okay. If I am increasing, sorry, if I am decreasing the Kp value, that means 0.1, the rise time value should be decreasing, which you can be observed in the previous case. Similarly, if I am increasing the Kp value, peak overshoot may be increasing. So again, for this, I am going to the previous slide again. This slide you can observe it. Okay, the topmost one is the peak overshoot value, and the downmost one is the peak undershoot value, and this is called the settling time, where our error signal is almost equal to 0. Okay, now again coming back to our table. If Kp value increases, rise time value increases, and if Kp value decreases, overshoot value decreases. Similarly, if Kp value makes a small change, there won't be any change in the settling time. That means if even the Kp values varies or decrease, there won't be any change in the settling time. If the Kp value decreases, the steady state error decreases. That means steady state error in the sense, let us take this curve from here to here, this point to this point, some gap is there. This is called as this position error is called as steady state error. Okay, so with the decrease of Kp value, steady state error decreases. If steady state error is decreasing, the stability will be degrading. Next, let us go with Ki. So here with the decrease in Ki value, rise time decreases, and with the increase in Ki, overshoot value increases, and with the increase in Ki, settling time is also increases. Similarly, with increase in Ki, the steady state error will be eliminated and the stability will be degraded. Coming to derivative, if you are increasing a slight change, the rise value increases and the overshoot value may be decreasing. Settling time also will get decreases. Steady state error, there is no effort, and if Kd value is varying, the stability value will be increasing. Okay, this is one of the comparison with proportional integral and derivative controllers. Next one. Here I have presented you the application of conventional PID controller. So if you look into this one, this is the conventional PID controller, where its structure, okay, where its structure you can observe it from here. This is the position of PID controller. Okay, this PID controller is having only one signal, that is error, which is the summation of reference values and the feedback gain. This is one of the most thing which it differs from the degree of freedom controllers. So after PID controller, a gain is provided, and after that, this is the transfer function model of a DC motor. Okay, are you getting it? 1 by 5.5s into 10 to the power 3s into power plus 0.8. This is the transfer function model of a DC motor. Okay, our ultimate goal for this is I need to maintain the DC motor at constant speed condition. Okay, so irrespective of the speed of the output condition, here somewhere the scope is to be connected. Okay, and this is the gain, and this is another transfer function. So for this one, the plots are drawn, and you can observe it from here. So on the x-axis it is time in seconds, and on the y-axis it is the amplitude of the error. So if you observe this one, these are the optimal parameter values. So for only PI controller, PI controller, PD controller, this is the red value, red curve, and for PI controller, this is the blue PI controller, it is the green. This is the blue curve. And coming to PID controller, the green curve you can observe it. So from this PI, PD and PID controllers, you can observe that the green one, okay, green one in the sense with the responses with the PID controller are settling, are showing less peak overshoot and less undershoot, and it is settling very fastly. Okay, settling very fastly when compared with other controllers. And for this, I have taken the reference as a comparative study between PI, PD and PID controllers, and this is an Arabic journal. Okay, from the Arabic journal, I have taken this as the reference. Next one, application of PID controller in load frequency control studies. So if you observe the block diagram, this is the load frequency control studies in which I have worked, my work is mainly on load frequency control only. Apart from that load frequency, I have worked on solar PV cells and electric vehicle management, electric vehicle battery management also. But here I was focusing on PID controller in LFC studies. Okay, so this is the PID control in LFC studies. So here I have introduced the PID controller. Okay, this PID controller, what does this PID controller does means it will reduces the deviations in frequency and tie power. Okay, and for this PID controller also, the others in this paper, load frequency control or assessment of a PSO PID controller for standalone multi-source system. Okay, this is Technologies Journal. This one published in 2023. For this also, we have introduced the optimization techniques. That means artificial intelligence techniques. Here in this paper, they have used particle sum optimization technique with PID controller. So here also the controller values are optimized with the help of PSO, particle sum optimization technique. Where if you need to optimize these techniques with the hand, it will take a lot of time. That means the I value is to be kept in mind, P values is to be kept in mind, D values is to be kept in mind, and where in such a way that optimal response should be get it. Instead of doing it normally with manual tooling, we can connect with this one with the optimization techniques, and the optimal results can be produced and developed. So for this, the plot is the graph is plotted, and you can observe it in here. Okay, here on x-axis it is time in seconds, and on y-axis it is frequency deviation. That means in load frequency control, whenever sudden load or sudden disturbance occurs, the frequency and taper values will be varying from the nominal values. For Indian standards, frequency will be 50 hertz. So it will be varying in the range of 0.004 kind of thing. Okay, so that we need to keep our system at nominal frequency, that means error of frequency is 0. So for that, this is the conventional PID controller which others have used. For that, different algorithm techniques such as conventional PID, means manual tuning. Next one is genetic algorithm, GA in the sense. Next one is differential evolution algorithm techniques. So this others have used PSO technique and compared with other algorithms like differential evolution, genetic algorithm, and conventional PID techniques. And if you observe the responses, you can see that the black color one, that means this one, is having less peak overshoot and less peak undershoot, and the settling time is very much less when compared to the other two algorithms. Okay, so here in this article, they have used the PID controller for the optimization case in order to reduce the frequency and type power deviations. Coming to the next part, it is proportional integral derivative with filter terms. In the previous time, I have told you that with the help of D controller, a noise is introduced in our system. Okay, this noise is an unwanted signal which creates an imbalance in the system. That means it leads us to instability case again. So in order to eradicate this, the authors have come up with an idea called a filter coefficient, which is to be introduced into the system after derivative gain. So this filter, what it does means, it will reduces or eliminates the unwanted signals that occurs with derivative. Okay, apart from PID, filter term which is added, and you can see this one in voltage gain controller also. Here you can observe this, a robust positioning of laser beams using proportional integral derivative and based observer feedback controller mechanism. So in this article, they have used the conventional PID controller also. And the transfer function of this PID controller, you can get it. KP means proportional gain, KI by S
that means integral gain, and for this path kd into n divided by 1 plus n by s. This is for the derivative term with filter coefficients, and its application is found in voltage gain optimization cases. So next part is fractional order controllers. So in conventional PID controller, we people are mainly focused in optimizing proportional gain 1, derivative gain 2, integral gain 3, and filter term 4. That means most probably 4 elements are to be optimized, 4 parameters are to be optimized. But when coming to this fractional order controllers, this we can say that this fractional order controller is an extension of integer order controllers by using some fractional controllers such as lambda and mu. These all are where lambda is called as integral gain parameter and mu is called derivative gain parameter. Let us see here. For our understanding purpose, I have taken a conventional fractional order PI controller. So this is KP, okay, which is similar to our proportional PID controller KP, and this is the integral gain KI. For this, in a conventional PID, there will be 1 by S term, but here S to the power of lambda is also there. If you observe this one, S to the power of lambda, I think you can observe it, S to the power of lambda, where this lambda values varies from 0 to 1. Are you getting it? Apart from this Ki gain parameter which varies from 0 to 1, this lambda value also varies 0 to the 1. If we assume that if a pole is located at 1 by S, that means at the origin 1 by S, system is marginally stable. If it is in the power of S to the power of 0.1, the stability may be increasing because the pole is slightly shifting towards the right hand side of the system. Like that, this lambda which varies from 0 to 0 to 1, the system varies. Okay, and the transfer function diagram and the transfer function model is shown here, and its transfer function is Kp plus Ki by S to the power of lambda. We are coming to FOPID controller, that means fractional order proportional integral derivative controller. Okay, proportional controller is same, and integral controller constant is also same, derivative control constant is also same with conventional PID. But you will find a difference between this integral gain parameter and derivative gain parameter. Coming to the integral gain parameter, it will be having S to the power of lambda, which we have discussed in FOPI controller, and the next one is S to the power of mu. That means even for the derivative gain parameter S, we are giving it multiplying with the power of mu, where this mu also varies from 0 to 0.1. Are you getting it? So the total transfer function is Kp plus Ki by S to the power of lambda plus Kd into S to the power of mu. In this, a total of 1, 2, 3, 4, 5. We need to optimize 5 parameters. Okay, that means first one is Kp, proportional parameter, Ki, integral parameter, and lambda, integral gain, Kd, derivative parameter, and S to the power of mu, that means derivative gain. These 5 parameters need to be optimized. Whereas conventional PID, only PID are the parameters which are supposed to be optimized. So like PIDN controller, here also FOPIDN controller will be there. This FOPIDN controller similarly the n structure will be placed at the PIDN structure, and its transfer function is shown here, Kp plus Ki by S to the power of n plus Kd into S to the power of mu into n by S to the power of mu into n, where lambda and mu are the integral and derivative gains. So in this we need to optimize Kp1, Ki2, Kd3, n4, S to the power of mu 5 and S to the power of lambda 6. Okay, that means a total of 6 parameters need to be optimized. In this, okay, in this I have taken these block diagrams from these 2 articles, which is a review article written by me, and the second one a review article written by me, which is having an impact factor of around 10.0, around approximately 9.8 or 10, and the other one is renewable energy sustainables, in which they have considered a fractional controller. Okay. Next one, applications. So coming to the research oriented, here I have given a fractional order FOPI controller, where its application is found in extracting the maximum wind energy from the wind turbine system. So if you look into the structure, from here you can observe that this is the wind turbine system, Okay, and here somewhere the fractional order, here somewhere the fractional order PI controller is placed, and the MPPT technique for harnessing the maximum energy and power estimation blocks will be there here. So the main ultimate goal is to extract maximum power from the wind turbine systems. Okay, here also we have drawn, the others have drawn a plot here, that is time in seconds versus reactive power. If you observe these graphs, you can observe that the QS, that means the reference value, QS star means reference one, and Q means reactive power, PI, that means with conventional PI control, with conventional PI controller, you are getting these many oscillations. The reason is the wind power is intermittent in nature. Due to this intermittent in nature, the proportional integral controller is giving huge number of variations, oscillations. Whereas coming to this black color one, FOPI with PSO technique, that means particle optimization technique, you can observe that it is almost equal to reference signal, okay, with a slight difference of sinusoidal in nature. That means this comes with an extra parameter. That means in FOPI we are having an extra parameter when compared with the PI. That means in PI we are having two parameters. In FOPI we are having two parameters and one gain. With this gain, we are getting much enhanced responses over the conventional PI controllers. And this article and this example I have taken from this reference from this article, that is application of fraction orders synergetic proportional integral controller based on PSO optimization to improve the output power of the wind turbine system. This is for scientific energy reports. This is from the journal Scientific Energy Reports. Next one is effort controller for electric vehicles. Okay, and this one I have taken from fractional order journal, and this is the title of the article. Here also you can observe that the FOPI controller is placed over here. That means in between bus system, in between the output of the boost converter and the battery. Okay, our main motive is to charge the battery with maximum power in this case. Okay, so if you observe this one, the responses here, this is with optimized FOPI controller, that means fractional order proportional order controller, and this one is conventional PI controller. So if you observe the responses here, the first graph is for PV power, both the case it is PV power and the x-axis is time, and in the second case it is a battery energy storage power, x-axis is time, and the third case it is y-axis EV power and x-axis time. So if we observe all the responses, see here in fractional order FOPI controller, the PV power is the oscillation PV power is very less when compared with conventional PI. Even in the case of battery storages, see here the oscillations are very less when compared with conventional PI. Similarly, EV power, it's almost a straight line here, but whereas in conventional PI you are getting some spikes. Okay, oh sorry, you are getting some spikes. So here also this FOPI controller has shown significant responses over PI controller, conventional PI controllers. Next one is tilt controllers. Okay, in FOPI controllers we have gain set, derivative and integral parameters, integral systems. But where in tilt controllers you are having these gains for the proportional control. So see, if I close this one, if I close this integral controller, the derivative, the integral and the derivative are almost same with conventional PI controller. Sorry, conventional PID controller. But the major difference is for conventional PI controller, here the gain will be KP. Here the gain will be KP, and for the integral term is not present in conventional PI. Whereas here in TID controller, the integral gain, for tilt gain, there will be s to the power of -1 by n. That means a pole is added for this proportional gain. Due to this one, that means this is similar. That means in FOPI we are having gains at P, I and D, but in tilt gain we are having the parameter at proportional gain. Similarly with D, we have developed a TADN controller. Okay, and this one, these two are taken from the reference of articles, both are written by me only. And this is the review article, first one. And the second one is design of TID controller based Firefly algorithm for the speed control of a DC motor. That means we are maybe it will be in the next slide, I think so. Yes, it is in the next slide. You can observe it. So here the TID controller is placed. Here the TID controller is placed, and this is the transfer function diagram of a motor. Our main motive is to minimize the error. How, where I am calculating the error means at this instant I am calculating the error, and here I am giving it as an ITS, that means integral time square error I have considered for the study. That means many errors are there, which we will be discussing about these errors briefly in on the third day of maybe on the fourth day of our course. So here I am getting the error, I am multiplying these things. So our main motive is to reduce the error. So if you observe this one, okay, the pink color one, I think it is clear, or else I will zoom it again. See here, I think now is the screen is with completely fair only. The pink color one is with reference signal, okay, and the red color one is with our proposed TID controller, whereas black color one is with PID controller, and with the blue color one is the blue color is one with PID controller, and the black color one with FO PID controller. So if you made a comparison of all the things, the red color one, that is TID controller, has shown significant improvement in settling time, where TID controller is settling at around 5 seconds, and this PID and FO PID are settling after 8 seconds. Okay, and there is no peak overshoot undershoot, so no problem. So with this TID controller, I am getting better response over conventional FOPI and PID controllers. Next one is degree of freedom controllers. So as I told you earlier, see here, for the controller we are having only one reference input, whereas degree of freedom controllers, as the name itself indicates, 2 degree of freedom controllers. As the name itself indicates, 2 degree of freedom controllers. That means we are having 2 reference inputs. That means 2 reference signals. So RFS is one reference input. I think you can observe it, this one from the slide. Okay, RFS is one reference signal, and YFS is another reference signal, in which you are given to PI, that means proportional gain, and I integral gain. That means this is the structural diagram of 2 DOF PI controller. Are you getting it? So that's why I have given the name here. See, 2 DOF PI controller. That means 2 reference signals are given to both P and I separately. See here, reference RFS is one reference, YFS is another reference. So see here some gain with proportional gain, and YFS directly to proportional gain. Similarly, it is directly given to integral directly, 1 by S. So for this, UFS is the output. So the complete transfer function f of s is equal to, with these 2 reference signals, this is the transfer function gain. Similarly, coming to 3DOF PID controller, and in this case we have considered a 3DOF PID controller. That means 3 reference signals will be there. The first reference signal is RFS, which is similar in the 2DOF structure, and the second reference signal is YFS. This is also similar to this structure, previous structure. The third reference signal is this feed forward network. Okay, this feed forward network. Now the structure is designed such a way that P, okay, I is up to the mark, and D, okay, that means PID design is same. For this PID design, we are giving the outputs from Y of S and N of S and R of S. That means each gain is getting 3 reference points from R of S, Y of S, and N of S. Okay, and for this, the transfer function is shown here. This is a transfer function model, and f of s is the output. F of s is the output, and these things I have taken reference from, as usual, my reference article which we have published in Turn Impact Factor Journal, and the second one is IETE journal, where we have used 3DOF TIDN controller. Okay. Now applications of degree of freedom controller. So coming to its application, as I am working on LFC system, here I have presented the 2DOF FOPI 2DOF PID controller. Okay, 2DOF FOPI fractional order controller, FOPID controller. and this is the thermal system, which we will be discussing these things afterwards. Now, as I'm completely dealing with MATLAB modeling, so I am discussing the controller part only. So, coming to the responses, if you observe the responses over here, first one is deviation in frequency with area 1, time is the x-axis. So, here also we have provided between 2 dy of FOPI, okay, that means fractional order PI controller, and 2 dy of FOID, fractional order integral derivative controller, and the last one is 2 dy of FOPI, that means fractional order proportional to derivative controller. So, if you observe the responses, you can see that the blue color one with 2 dy of FOPID is showing less peak overshoot and less undershoot, less peak overshoot, and settles very fastly when compared with 2 dy of FOP ID controller and 2 dy of FOID controller. Even in the case of type power also, you can observe the same responses over here. Okay, so this is one of the applications of degree of freedom controller. Next one is IBC inverter. That means for the extraction of maximum solar power energy among DC-DC converters. This is a structure diagram. Here, the others have placed the FOPI controller. Okay, this FOPI controller is linked with some algorithms, and they have proposed and they have made a comparison. Okay, and they have made a comparison with ASO algorithm with conventional PID controller. That means in this work, the authors have considered 2 DOF PID controller, which was optimized with ASO algorithm, and the responses are compared with ASO algorithm with conventional PID controller. So you can observe the responses over here. Here in the responses, you can see that on y-axis it is voltage and x-axis it is time. The pink color one is the reference signal. Okay, and apart from reference, the green color one is conventional PID optimized with ASO algorithm, whereas the blue color one is with proposed structure. That means our ASO optimized FOPID controller. Sorry, ASO optimized 2 dy of PID controller. Sorry, it is 2 dy of PID controller. So this degree of freedom controller is one better responses over conventional PID controller, and also this is the algorithm which this is the article which I have taken from Electronics Journal. Next one is intelligent controllers. So as we all know that the intelligent controllers, fuzzy controller, next one is neural network controller, and the other one is model predictive controller. But here I am discussing about fuzzy and artificial neural network controllers. So coming to the fuzzy, in order to understand the concepts of fuzzy, let us take an example. Let us take a group of people of various heights. That means let us take a group of 10 people in which height varies from 5 feet to around 7 feet. Let it be 6.5 in terms of practical. So 5 to 6.5. All the people, her height is not same. Each people is having different heights. So let us take a first person who is having of 5 feet, and the second person who is having of 5 feet 1 inches, and the third person let it be 5 feet 2 inches. That means each person is having a difference by 1 inch or 2 inch or 3 inch. Now how we can differentiate? If you assume that 5 has less height and 7 has more height, okay, that means large and small kind of thing, and you can assume it as 6 as medium. But if it is 5 to 5.5, this people comes under small means it is not small, because each person is wearing different. So for that, they have developed a membership function over here. This membership function is given by this membership table. Let us take an example. See, we are having two elements, that as N and P. Out of that, L means large, M means medium, S means small, okay, and E means neutral, let it be, and again S means small, M means medium, L means large. So two parameters N and M with error and differentiation in error, that means deviations in error. So if a person comes under NL, that means N is that means large, he will be called as large person. And if a person comes under large and medium, in between large and medium also you will be considering it large. In between large and small also you will be considering it as large. Like that, they have developed a table, membership table, such a way that each person will come under each category, different categories. Okay, this will be little bit difficult to understand, but this completely works on the membership function and membership table. And the next one is artificial neural networks. This artificial neural network structure is similar to our brain, is similar to our neurons in the brain. So you can see this is the input layer, and this green color one is the input layer, and the orange color one is the output layer, where many hidden layers are there. This is the hidden layer one, this is the hidden layer one, where you can establish many connections between this, and you can give in the one output. Okay, so many internal connections has been there, and finally one output will be get. So this is the structural diagram for artificial neural networks, and this is the membership function and membership table for the fuzzy network. So I have taken this for these articles from these three references. First one is as usual mine, and the second one is introductory survey on fuzzy control and a multi-layered neural network controller. And coming to its applications, this fuzzy can be implemented in robotics, where with the help of conditions if and then. Okay, that means you have to raise a hand of a robot or do some work with the robotic operations. Next one is a wind turbine system. Here also we have used the neural network, in extracting maximum energy for the maximum energy from the wind systems. Here also we have given the comparisons. You can see that conventional PI is with black color, and fuzzy neural network is fuzzy logic controller is with the blue color, and red color one is the cascade combination of artificial neural network with fuzzy interface system. Okay. Next, cascade control block diagram. This is the final part, and as we are lagging by time, we will be concluding further. So in cascade controller design, there will be two controllers which are connected in parallel. So this is the first C2 of S is secondary controller, where C1 of S is the primary controller. The secondary controller now you can can observe it. This C1 of S is the primary controller and C2 of S is the secondary controller. This secondary controller is in inner loop and the primary controller is the outer loop, where G2 of S and G1 of S are the plant transfer function models. Okay, so here you can observe that there are two controllers. One controller will act as master controller. This one will act as master. So this one will act as slave, and the primary controller acts as master controller. So if you observe the diagrams here, I have given you the cascade structure of PI with PD controller, and this one is PI with PIDN controller. Okay, that means two controllers are getting cascaded. The major advantage of this is it is having two control loops in which output error is further reduced. And this is the response in terms of cascade controller. This is my first article which I have published in around 2017 and came on in 2021. This is the FOPI controller PIDN. This is the proposed. Sorry, this is my third article, FOPDN with FOPIDN controller. So if you observe the responses, the cascade controller structure has shown better response over other controllers. Okay, because of two loop structure. And another one is of okay, and another one is for deviation in type over. Coming to the next one, here I have provided with the benefits and drawbacks of different kinds of controls which we have discussed so far. First, coming to classical controller, the classical controller in the sense conventional PID controllers. The benefits are it provides quick transient response, less cost, but its drawbacks are the poor performance. Coming to intelligent controllers, model is very bit complex, but it gives exact and accurate responses. It has a drawback of handling weak limitations. Coming to freedom controllers, it has enhanced system. It enhances system stability by eliminating the errors because it is having more than one reference set points. And the drawback is as the control loop increases, the complexity is also getting increased. And the cascade control structure, two control loops are there, which are more advantages. The major drawback is it is slow because of its second control system. And the next one is model predictive controller, which I haven't discussed, but it is also one of the advanced controller which works on design and controlling the model and predicting the models, system model, and sliding control system. Apart from that, here I have provided some of the various controllers in the MATLAB. First one is integral controller, second one is PI controller, third one is PID, fourth one is PIDN. Here PI double D controller, that is proportional integral double derivative controller. This is integral derivative double control controller, and this one is integral double derivative filter, and this one is integral minus integral minus proportional derivative controller. So here are some of the controllers which I have personally implemented in my research area. Okay, with this we came to an end. If anyone is having queries, we can discuss it now. I think no message in the chat box. If anyone is having queries, they can text in the chat box. Okay, then as we are lagging, as we are running out of time, as the time has surpassed 8, I'm concluding today's session, and we can continue the tomorrow session. Thank you all for listening patiently. Thank you.